Hi everybody, today we explain the theorem we spoke about last time, about the curvature and complexes. So our setup was d omega real symplectic vector space of dimension 2n lambda was the double cover of the symplectic group then we chose a Lagrangian subspace maximal isotropic in V. This is parallel to spin n covering SON, but these groups are non-compact and moreover G is non-matrix. It doesn't have faithful finite dimensional continuous representation. That's all. And we have this symmetric to Rn, and we denote it probably by rho. Not specific unitary representation in the symplectic group on the space of L2 functions on L with respect to symmetry, which is chosen. Unitary group. This space will be often denoted by S. Space of symplectic spinors. Then we decided to investigate this space. Vector forms, base values in symplectic spinors. Sometimes also called twisted by symplectic spinors. The representation here is still denoted by rho. Is given as follows. We go via lambda to the symplectic group. So we are in a space, acting on a space Rn, R2n. We take a dual in order to act on forms. We multiply by the spinor. We are speaking about groups, not about algebras. So this formula, this is a bit confusing, I agree, so I must add some sign, which I hopefully not forget. So this is understandable. So dot lambda is a map from SP P omega 0 and P omega 0 to SPD omega 0, which is a subset of automorphisms of dual representation means just this. Lambda is homomorphism. It's not only covering but also homomorphism. So this is a setting. Then I mentioned last time was I mentioned that we would like to decompose this space into irreducible spaces. So actually, let us introduce the following set. C, sorry, of non-negative integers paper. And with this notation, we have a theorem for any n bigger or equal to 1, E is written as a sum of subrepresentations. I will denote them by lower indices ij. Ij is from the sub psi. Each ij decomposes into just two non-trivial irreducible representations. Each Aij is a submodule of the piece product and S. Sometimes I write star, sometimes not. So this can be achieved by using similar formulas as Klimek and references Janssen, Karsten Janssen for the formulas. Or this is in my article, this is computed in article like 0.5. There are two articles in the Journal of Lead Theory. One is older than 2010 and one this is the article. So formulas by Janssen. Attributed to cuts. So that you can pick up formulas and decompose. Okay, so now we shall, before we induce these vector spaces and G tilde modules to geometric setting, there will be further convenient operators which we can introduce. So definition. Operators define on symplectic spinor valued forms. So some constant, they are given by such formulas. I will explain what the dot means, or what the epsilon means. So omega ij is just omega ij with respect to a symplectic basis ei. Ei symplectic basis. What is the dot? Vector times symplectic spinor is prescribed by the so-called symplectic spinor multiplication, which differentiate and multiplies. One shall be usually careful what it does when I can say some formula which I usually there are more possibilities. Maybe it will be here. So the first n EIs acts by this. And the next I So this is defined on the short space, actually only. So it's not defined onto L2, obviously. So here we are already using the p-work on the short space. There are some problems with that, but they can be technically omitted, and it's well known how to get rid of these problems. So here, so this is a symplectic Clifford multiplication. It reminds us to canonical quantum quantization, canonical quantization prescription. Impulses differentiate and coordinates multiply. So this is an interesting multiplication. Let me say briefly some facts. Similar to what you know from Riemannian spin geometry. In Riemannian spin geometry there will be opposite sign, there will be probably no I, and there will be G 0. Yeah, so this is known for Riemannian geometry and spinors. Important is the equivariance. I can act by representation rho on vector times spinor, and I get the same as I would act by G on the vector times representation on the spinor. So
there's S missing.
S is here and S is here.
On the previous line, last bottom
S
line,
is
no,
here.
last bottom line, yes, to the right.
Okay.
And on the right hand side, there is S missing.
So these are pure algebraic formulas. So now we probably can understand this formula better, not yet, but only better. Not completely, but only better. Epsilon j with the basis dual to the basis ej. This is inserting EI into alpha, insertion of EI into alpha. And it can be proved that these operators are equivariant. With respect to rho tilde. Moreover, if one defines, so it's the same arc, moreover, the whole commutant of intertwining operators on this E is just span of F plus T times and F minus T times K times. And I shall be more precise, or either I should add there one operator more. They are algebraic spans, meaning we can also form these things. So algebraic, it is an associative algebra span. Observation is, and this was not known, that defining certain operators E plus minus by formulas which are rather obvious up to some constants. So I will have a look. Let's start with this. For example, so if I define this, I say what it means, these double brackets, then the linear, really linear span of, how to write it, E plus H, A minus, F plus, F minus, forms super or Lie superalgebra OSP 1, 2. This corresponds to the Schwabach F0 part and this to the Schwabach F1 part. So this is some kind of algebra. It has a Z2 grading, meaning that as a vector space, it is a direct sum of F plus, F0 plus F1. And there is something, so this is super vector space. And there is something like a super bracket, which in this case is just a bracket minus 1 times degree x degree y yx if x epsilon are from f0 f1, so especially they must be only in one, or they cannot be, they have to be in one of these summands. They cannot be in some non-trivial sum of these summands. The degree must be defined. Degree For other elements, it is actually defined by linearity. So this is a formula for supercommutator. X and y cannot be zero. If x is zero and epsilon is zero, everything is zero. Because degree of zero is not defined, zero being in both parts by spaces. And it's everything than zero. By the way, this F0 part, is isomorphic to your famous algebra SL2C. And then F1 is a F0 module by X, Y, just being supercommutator X, Y. And adding one cubic equation, we would get to the general definition of super Lie algebra. We don't do it yet. This is sometimes this F0 is sometimes called bosonic part, and F1 is sometimes called fermionic part. So super vector space, vector superspace. Super associated super algebra and Lie super algebra. It has two definitions. First one is supercommutativity. Then there is a super Jacobi, which is just Jacobi ruleless signs.
Too many brackets.
Yes. BC might go in this way. CAB
So in the middle term there are also too many brackets.
in the middle.
In the middle term.
Thanks. I know there are some signs. I guess these signs reflect the outer elements. This is one definition. Second definition is that it is a vector superspace with a bracket such that the bracket as stated on the first part of the supervector space is just a Lie bracket. Is a Lie bracket. And F1 is a F0 module. And a cubic relation is satisfied. There are more conditions, and I'm sorry, no, I will not give them. So the message is that they are somehow derived from the ordinary Lie theory. These super Lie algebras might be. So we found a commutant all maps which commutes with the representation rho on those wedge forms with values in spinors. They are given by these operators, which are the substantial part of substantial in the sense that they generate the whole of SPS. F plus was, big F plus was sufficient to define all the other elements. So this is the full commutant in this space. So, and it's quite good to have this commutant, as we will see later, hopefully later. Spoke about the curvature. So let us recall it briefly. What is a curvature in the symplectic case? second item, curvature. The defining formula is the same, and I will not speak about it now, as in the Riemannian case. Convention for lowering indices is here, this one. Now, symplectic Ricci tensor is defined by the same formula as you know from Riemannian geometry. And sigma ij will stay the known. Yes. So now we are on a symplectic manifold, so we are out of the vector space setting. So we may stay on symplectic vector space. I consider it as 0. And Ui is a symplectic frame. In each point, a symplectic basis. This vector space. The curvature tensor R has one similarity with the curvature tensor of a Riemann connection, namely it is antisymmetric with respect to the first, with respect to these indices KL, so with respect to the last indices in this setting. Otherwise, there is no antisymmetry in this, there is rather symmetry in this. How to define the Weil curvature? So the formula is, consider the extended Ricci curvature, which is a tensor given in coordinates by this formula. Fortunately, I haven't worked with it. I haven't worked with it for a long time, this while, so I will just rewrite it. But certainly it has some remarkable symmetry which you can keep track of. So this is the extended Ricci curvature. It can be proved that the definition doesn't depend on coordinates, yeah? So you can define them. And taking another basis here, expressing the sigma and omega with respect to another, different basis. would lead us to different sigma tilde. So here these numbers could be possibly different, but these bases will be also different in the way that it cancels the difference. It must be proved, or it is more or less visible. Physicists would see it immediately because they would write probably ij up and kf also up, and then it's more believable, but nevertheless one might check it. Yeah, and the while is easy. While is just the curvature minus this type of curvature. This is the while curvature tensor. And we said that we can build a complex if the while curvature vanishes. And you specify the complex. The same is as the while the symplectic curvature is of Ricci type. If this vanish, this is trivial, then N becomes just this sigma, which encaptures this Ricci part. So go to define operators. I don't know whether it will be really the most convenient version that I present, but let us try to say it, even if it's further formulated. So now we have a space to do physics or geometry or topology. We have the connection which is symplectic, might or may not be torsion free. We suppose that it is torsion free. We know that there are plenty of these connections forming the space of sections of the self-symmetric over of Tn. Let me start. Okay. Then we can induce the connection to forms with values of a bundle. And we will do it for the associated bundles. So now we would like to differentiate not only, as here, differentiate not only vector fields, but also vector fields or forms with values in a specific bundle, distinct bundle. So we think of connection to associated bundle, which we probably denoted by S. S is the associated bundle associated to the metaplectic, to the Segal wave representation. P was what? P is already the double cover of the bundle of symplectic frames. So now the machinery of bundles comes into play in in very standard way. So I call it. So P and P Q SP R Q P and here we have lambda, the next variable coming into this framework. This is lambda, the covering of the groups. Here are projections, P or Q, P1, P2. And here are actions of NP on P. So this is the definition of a principal bundle, the first row, first and half. This must be also a principal bundle, and together they are joined by this lambda times small lambda. So if there exists a big lambda and a bundle P, then this diagram might be named metaplectic structure. First P, then lambda. It is, as I said, it is something that big lambda is a morphism of principal bundles, two with different groups. So one doesn't say it in this way. So this is a morphism between MP principal bundle and this is SP. So actually it means with commutativity to explain that it really might be seen as a morphism, So I act on an element R from P by group element G. Then I apply lambda. This lambda. And it is the same as I will do times this. Sorry for being long. So this is actually up to the covering is up to a covering it is a morphism of principal bundles. If lambda wouldn't be here, then the formula is actually exactly the same as you know from principal bundles. So this is the situation. Since P is an MP bundle, any representation of MP can be associated to it. We replace the fibers isomorphic to groups by the carrier of the representation, by the vector space the representation acts on. So again, it's written here. I rho L2. We would like to consider operators on such sections, non-trivial operators on such sections. First well-known one was the symplectic Dirac of Habermas. Of Katarina Habermas. There are also second Dirac. There is something like symplectic Laplace, Bochner Laplace. So further operators developed to investigate this operator D. We will see this operator as a specific case in the picture. Using the picture, we drew yesterday. Oh, I mean last week. So I will recall it. Yeah. So now back to the machinery. Nabla symplectic connection on tangent bundle. It leads to a principal bundle connection on Q, which is SP bundle. This is, maybe you know, this is the Cartan point of view, yeah? So instead of connection, you consider connection forms, and so this is precisely the matrix valued connections. This can be lifted to P. This is somehow by triviality of liftings. This is quite normal. I wouldn't like to do these computations, but there are formulas for that. How to lift it. I never did it by hands. We get a connection denoted Z prime, Z hat, and then MP principal bundle connection lifts, induces, better to say induces, a connection on the associated, on the induced bundle S. And there are also quite nice formulas for it. Yeah. So, starting from symplectic connection, we get here and actually, though as we presented it already in this stage, in this phase, to this point, so we can actually give the definition of the Habermas Dirac already with all the picture actually, since you saw. Now, this can be combined. I will write Nabla as here. There's the symplectic Clifford multiplication is differentiating and multiplying, which you see depends on the basis actually, the definition. But it was on the other hand equivariant. So if it is associated, then it is well defined on the manifold. If it is put onto the associated bundle, it goes just through the relations. So the relations you need to verify, you need to satisfy. So here we get spinors. Actually here, I don't know why, but to be more geometric, let us make first this thing. Sorry, minor change. Actually, I don't understand it, but if you see it, then you can see, oh, there was a mistake. What one does first is that one identifies the cotangent bundle, which is really here, with the tangent bundles, and this can be done by omega or by a chosen Riemannian metric, and just as these rising operators and lowering operators in music. And now you can apply the multiplication in both cases. Yeah, we multiplied vectors by spinors by vectors, not covectors. And we can do it in the two ways, yeah, with two identification with either with G0 or with omega 0. No, for sure, these composing, right here. Composing this operator, these operators, one gets the first Dirac, or first symplectic Dirac, and here one gets the second symplectic Dirac of Habermas. So this is the definition. Maybe she uses different notation. I know where she studied, so I know that she writes here as symplectic. Now, if we do similar things with inducing two bundles and induce nabla via Z, via Q, via pi, up to not only S but to E, denoting this bundle EI.
So twice the M should be there. And the two lines.
Here, okay, you're right. Here we make the multiplication. Here we make the multiplication, so the vector disappears.
The same symbol.
Yeah, exactly, if you are not mistake. So the vector times spinor is spinor. Yeah, so here we have S times V, and we produce just V times S. Now this is what is by this arrow meant. So otherwise, it's not clear what's going on actually. We can let that vector be, but it's better too. really to have only spinors.
So what is G? What is that arrow G in the middle?
Arrow G is symmetric.
And how it can be symplectically invariant?
No, it's I don't claim that it is symplectically invariant. Usually you choose a complex structure, and then it will be more a representation theoretical to see easily in this way that you have ST, you choose U in N, you choose UN, and do everything by U to UN, and it stays the same because it is a retract. So the association.
So D2S is not symplectically invariant.
But I think that it shall be. I never use this D2 actually. They are used in the Keller case. Katarina uses certain in the Keller case. But I must also say that I'm citing just her book yet.
Oh, the first row is obviously symplectically invariant.
This is okay.
The second row is obviously not.
Two, it doesn't make sense. What is it symplectically invariant? Since there is no natural group action. Well, I understand. It is well defined. Philosophically, or maybe you're it is well defined. This is what I say. It's well defined. Because a priori there is no group acting if you don't do trivializations or if you don't suppose some homogeneity of the situation from the beginning, meaning the manifold M is a G over H, something like that. G is symplectic or metaplectic or unitary. So a priori there is no group acting, so it's everything else somebody told it to me, about in well-definedness. Invariance is not.
If you have symplectic manifold, metaplectic manifold,
I can act on
then
the principle bundle.
you can act on frames by
Yeah.
symplectic or metaplectic transformation.
But I cannot
that's what it should be.
I already cannot act on the associated bundle. Because this is really not possible, and neither on the sections.
So why you cannot act if you have
It is some obvious known fact.
Probably some.
Which I You can think of it later, probably, but not yet. No, it's in general it's not possible. It is about well-definedness. Yeah, so invariance. When physicists speak about well-definedness in case of Dirac, they can say, okay, I turn the observable and the measuring device. I turn it by a Lorentzian transform, and then also the wave functions changes, and then the Dirac will be different on these wave functions. But then I must take it back to the ordinary state of the measuring device, and I recompute it, and I recompute it well. This is invariance anyway, with respect to all. This is not, it's not so visible maybe, but it is invariance. But they speak about R4, where they have global, really global actions of the group, SO13. This is maybe what reminds you something. I don't know. Homogeneous situation, one can speak about it. Okay. associating, we get D, E acting on EI, or acting on, define on EI, this target EI plus 1. So this is by the formula we spoke about. D alpha times S is maybe number, I will put here number in order to say that we started with a symplectic connection. This is the RAM on the front bar plus sum of epsilon alpha nabla EIS, where S is a spinor section.
That's script S, because you denoted it before by script S, that connection.
Okay, too much S's.
But there is a use, right? So on the second line there is nabla superscript S. That's not over arrows. Over there. On the left. Yes.
No, this is S, you're right.
Script S, and that's the definition on the most left part of this formula. So use nabla S.
But everything is in use. So it looks
So you simply cannot expand it in the basis, so you simply can write alpha O times nabla S.
Okay. I will write it only here. Do you agree with it? But I will write it only here.
Okay, it's like.
Where epsilon I and EI are dual bases. So this is a formula from which we see that I form of degree I is transferred to form of degree I plus 1.
So the sum is up to n or up to 2n? Up to 2n, right?
2n. We can restrict, let me use this place, we can restrict VI two sections of gamma Aij and project it two sections of EI plus 1 K, where P I plus 1 K is just the projection of EI onto EI plus 1 K. Now this can be done either by some orthogonality, which we haven't introduced, but it would be, I think it shall be possible, or easier by representation theory. So let us come again to the decomposition, where these bolded EIs are hidden, or these curly EIs are hidden in the normal classical capital EI. At the beginning, I spoke about set psi about an index set aside, which helps us what? Which helps us to decompose, which helps us decompose this E into irreducibles. Let us take a specific n is 3, so example, before we continue on these projections. N is 3, we have 0 forms, we have 1 forms, this values in spin-offs, which I omit, and so on. How do they decompose as submodules? We can go up most to n minus I j. The second index has such a limitation. So if you compute it carefully, you see such a picture by which we can see further structure of these modules. And now we can go only up to 3 minus 3 minus, this is 1, 3 minus 1 is 2. Yes, okay. 2. E50, E51, E6, 0. Plus we can note again that each Ej decomposes into the sum of irreducible. Of course, every indices shall be done. Sometimes I write it. Nothing, no duality here is involved. And what is known? These, taking each row, all of them are isomorphic. So this is isomorphic. And in each column, each elements are not non-equivalent. So in a representation, one speaks about equivalence. So these are equivalent. These are mutually non-equivalent in each column. So this can be expressed in this way. For each j, but taking control in order one doesn't arrive at 0. So sometimes if you have 7 form on 6-dimensional vector space, you will get 0. So I don't write it. And obvious by counts. Again, you can write on all these lower scripts. Okay. So now we can make the diagram curl. Calligraphical. We can speak about the. We can change all the letters into calligraphic. Why not? I will do it only with some of them. And then we have there these connections. Oh, actually, the name for it is associated, what is DE, DI, nabla associated covariant derivative. basically infinite geometry, and having the symplectic setting, symplectic covariant derivative, probably metaplectic covariant derivative. Metaplectic covariant derivative. Yeah. So let us consider covariant derivative on the second element here. In principle, EI is 2, it can go to all such elements. First result is, which I didn't formulate it, that if we restrict the connection, in the covariant derivative to Aij, its image is here. I must write sums very well. So this is first information. So non-trivial is it cannot, when restricted to 0, it goes to 3, 0, 3, 1, and it cannot go to 3, 2, it cannot go to 3, 3. There is nothing in the image. Blah blah. So this is first result. This is also the composition, also Janssen on cuts, and this was done in Journal of Lee Theory. The second article of me in Journal of Lee Theory. I have two there only, and this isn't the second. The first was mentioned. Joe, Journal of Lee Theory. Helderman Verlag. Some old-fashioned, not a big publishing house. Okay. So this is first thing. Second, can we project on the images? Yes, if all are non-equivalent, we probably can. Or even if we have this is a bit nonsense. Even if we have a direct sum decomposition, which we mentioned, and we label it correctly, we can project. Just defining P on the sum be the specific element in the sum. So even that we don't need to know that they are inequivalent, but it's somehow, I don't know, really easier. I am satisfied with it as it is. Is it okay that I can do these projections whenever I have it? For example, it would be problem if these were, for example, these two were isomorphic and I didn't know how they decompose into two isomorphic distinguished, but distinct. But this never happened. This doesn't happen here. Even that doesn't happen. Okay, so we can have, sorry for this small detour. We have this projection, and we can form these operators by I plus 1. Okay. We would like to see Dirac in this picture, the Habermas Dirac in this picture. The Habermas Dirac in this picture is the zeros covariant derivative, but you can see, one can see that it has images also here and here. and one must apply the operator. I denoted it by F minus, probably yes. F minus, sometimes I denote it by Y, but this much I denoted it first. So up to a multiple, constant multiple, the Dirac of Habermas is defined as a composition with symplectic for multiplication covariant derivative is nothing but the zeros covariant derivative with this low degree lowering operator F minus, which was inserting bases multiplying by omega j. F minus alpha times S is to the multiple 1 over 2 omega ij EEI alpha times EJS. So this is how this operator can be seen in this picture. There are further distinguished operators, not only the Dirac. But also so-called Twistor operators. What are Twistor operators? Typically, let us start with zero forms, just with sections of the symplectic spinor bundle. Twistor spinors, by an analogy, I must say, I don't need to say it, but I said it by analogy to Penrose's twistors, Twistor operators. It shall be mapped from here to here. This approach of Penrose was generalized by many mathematicians, and they took also, maybe he as well, I don't know it yet, also these operators has names Twistor, so they are going on the edge here. From the point of representation theory, there are also, we can also take covariant derivative here, restricted on one form, restricted to this space, and then take only this operator, and so on. So such so these are called Twistor operators, these are higher Twistor operators. And one can hope with this operator that you can do cohomology. Yeah, so, but first you must find a chain complex. So denoting these operators just what are they? Restrictions and projections. I don't have a good notation for it yet, so I have it in, maybe I find it. Right, so wait a second. Maybe here. Okay, I have it here. Pij plus minus is D projected to Pi plus 1, J plus minus 1, and here is restriction to epsilon ij. By plus minus, I didn't draw also the rising, the uprising. I mean, the Twistor operator is going up. Also operators going up, but only one times up. Even, by the way, they cannot go more because of this decomposition term. I only don't take this because they are similar to the other, which goes in this way. In the diagrammatical way of thinking. So, and now we shall compute Tij plus minus, let's say, composed with Ti minus J minus 1 plus minus. Projections, covariant derivative, projection, covariant derivative. So, one shall know the formulas for the projections, but this would be one shall. I think to know formulas for the projections is by no way easy. I said it in this way, but one can do several takes for which we don't. I'm running out of time. Yes, right? I just outline it, or I just say minimum. The trick is to put these deltas somehow together, which I thought we will speak about somehow, and see the projections of this DD, which is actually can be seen easily as a curvature of the chosen connection. That these projections of the curvature cut out the Ricci part, and only the while part stay. So if we, on the other hand, suppose that the while is 0, we get this as 0. Yes, so if this equal to while, and in the theorem, the last one was if while is 0, then it is a complex. So it's precise that this is precise as a statement. The problem is to compute this expression. Yes, it's some more difficult than in the case of Dolbo bicomplex or in other complexes. So it looks like technical, but on the other hand, it is somehow like not so obvious complex. So also the curvature computations are not easy, probably. So that's all for today. So you can find it, I think, on slides from Srni. I don't know whether I will continue next time, so it would be nice to find these formulas, because there are really nice formulas using using this decomposition, and how the Ricci part transfers, and what while does. I mean, what while maps where, and so on. So there are actually things which go out of algebras, representations, and superalgebras. Yeah, some symmetries which we can formulate, but at least I don't have name for them, so maybe you know them. Symmetries of this small sigma, of this tensor sigma, and tensor big sigma, capital sigma. That they bracket and anti-bracket, but not into some not to superalgebra. I would know, maybe by no means to any superalgebra. So actually, and this is where I stop. Maybe where you can find it. I write too long introductions when I recall everything. Yeah, so it's maybe boring, but it's monads have that. It is in a strange. It is in a journal. It is on camera. So it is a nice journal, not strange. Strange is really the name. Monads have that. Here mathematique. Yeah. So, like monthly, mathematic monthly. So there are, and I have only one, I guess, the articles on my webpage, and you can freely download a preview. I have done too many mistakes in the previews, and I don't know whether you can download real morals and stuff from the faculty. Maybe yes. Also, there are polished versions in the journals more than in the preprints. So complexes of Twistor operators. There is this computation done. Some basic tricks are to shift by x to the right and by f plus and f minus to the x to the left and right. And then sometimes if you are too much to the left, then f plus gives you 0. But here, f minus gives you 0. f0 gives you 0 already here. So these are the basic tricks. Use a commutator. And f minus, they are equivariant. I didn't say they are equivariant with respect to the representation. F plus and f minus. Okay, that's all for today. Are there any? We have some questions. So not. Okay, so next time we will maybe send email because we don't know what happens. Is it okay? So I will end it.